In the last lesson, we learned about what confidence intervals are, and we learned that when we're calculating the margin of error, we can control how big it is using the confidence level, which makes us more confident, right? So if we have a higher confidence, that would mean we have a larger net. If you can just imagine chasing a butterfly around with a net, the bigger your net is, the more confident you'll be that you'll catch it. The sample size also affects the size of the margin of error. We have better accuracy when we collect more sample values, so this produces a smaller net. If you can imagine having a better skill level, you would need a smaller net. You wouldn't need such a large net. So confidence increase equals wider interval, and it's calculated, or the margin of error that is calculated using the critical value, which could be a z-score or a t-score depending on the situation. And if you think of it as a z-score, because we're more familiar with that at this point, it's a z-score. And remember, a z-score tells us how many standard deviations away from the mean we are. And the SE here stands for standard error of the sampling distribution. So this is the standard deviation of the sampling distribution. So what we're basically doing is we're adding the standard error a certain number of times. How many times? Z times, for instance. So notice that if we have more confidence, that's going to push our critical values out towards the tails away from the mean. So that in turn pushes the margin of error larger and pushes our boundaries farther out, making a wider interval. The sample size equals a narrower interval, and we can see this because of how, again, the margin of error is calculated using the standard error, which has the n in the denominator. Now, you know, if you have a bag of M&Ms and you're only dividing it amongst 2 people, you're going to get more M&Ms than if you had to split it up amongst 10 people, for instance. Splitting it up or dividing by a larger number gives a smaller amount. So you make your distance smaller by increasing your sample size. So with better accuracy, we have a smaller net. The sample size n in the denominator causes us to move a smaller distance from the center. Now, what about choosing the sampling distribution? First of all, we ask, can we even use a bell curve for this? We want to estimate a population mean using a sample mean, so we need the distribution of sample means. And we know by the central limit theorem that the sample means will be normally distributed with the same mean as the original x values and the standard deviation divided by the square root of n, or in other words, again, the standard error. This is true if either the sample size n is greater than 30, or if the original population is normally distributed. So we check for that. We check the central limit theorem, we make sure it applies. That way we know we can use a bell curve. Now, if we know we can use a bell curve, we still have another choice to make. We have to decide between using the z-bell or the t-bell. The z-bell is the standard normal distribution with a mean of 0 and a standard deviation of 1. And you know the z-scores are on the horizontal axis. And so if we're using a z-curve, then we will have critical values that are z-scores. If we are using a t-distribution, that will also be bell-shaped. The mean is 0, but the standard deviation is not 1. It's usually close to 1, but it varies with the sample size. And we have a certain number of degrees of freedom equals n minus 1. So the sample size directly affects the shape of the blue curve, which represents the t-distribution. The red curve that's shown here overlaid with this is just so that we can compare it with the standard normal distribution. The t-distribution is so similar, but it is different enough that it changes the amount of area under the tails and therefore changes the location of your critical values as well. And if you have a large enough sample, then the blue line and the red line will match up. So in general, we use the t-test whenever we don't know sigma, the population standard deviation. If that's unknown, we'll use the t-distribution. If we have a large enough sample, we might not need the t-distribution since it'll be just like the normal distribution at that point. but I always say go on the safe side. And if you don't know the true population standard deviation sigma, or in other words, if you only know the sample standard deviation S, then use the t-test. That's the only time you have to use the t-distribution. Otherwise, you'll be using your z or your standard normal distribution, and that's for means when the sigma is known, or if you're doing an estimate of a population proportion, which is another lesson. So what about the empirical rule for sampling distributions? Would it be applicable for the mean of sample means, for instance? Well, with the regular x values, the empirical rule says that we would expect 95%, this area in between, to be within 2 standard deviations. In other words, between the z-score of -2 and +2. And we also know that we could have a correspondence on the horizontal axis where we could have x values, or we could turn them into z-scores using the z-score formula. Now, compare that with the sampling distribution with a pile of sample means. Well, if you recall, when we learned about the central limit theorem, we learned that because we have to use the standard error, which is the standard deviation divided by the square root of n, that makes your standard deviation of the sampling distribution smaller than it would have been for the regular x values. So it squeezes things in and makes it more narrow. And so your areas are going to be different, and what happens is we end up with smaller z-scores with that area of 0.95 between. So the empirical rule doesn't really work with the sampling distribution. What about the t-distribution? The t-distribution actually allows for a wider distribution with small samples, and when we only know the standard deviation from the sample. And so it's a little bit, wider, and the areas are larger under the tails. So it actually pushes our critical values farther out. Right, so there's just something interesting to note. We have the horizontal axis, which are t-scores, and notice the formulas for converting an x value to a t-score, just subtracting the mean and then dividing by the standard error, which is very much like what we did with regular x values. We can use any confidence level we want to, but the common choices are 90, 95, and 99%. Now, what about constructing confidence intervals? We'll get into that in the next video.